Okay, so thank you very much for the invitation. So I'm very glad to have a chance to speak here. So this is my title. And first of all, I want to explain the motivation. Well, maybe this is quite well known. And so I start with Coleman's theorem on the classicality of p-Adic modular forms. Okay, so you fix a prime p, and suppose you have an integer n greater or equal to 5. So, and this integer is you just choose large enough to guarantee that you really have a modular curve. Okay, so and k is greater than 2, so n is prime to p. Sorry. Okay, so and in this situation, Katz has constructed in 1973 the overconvergent p-Adic modular form of level gamma 1 n. Okay, so this is an inductive limit of p-Adic Banach space over QP. So it's infinite dimensional. And over this space, there is a complete continuous operator called UP and operate on it. And on the other hand, there exists an injection from the space of classical modular forms of weight gamma 1n, and there is gamma 0 p level structure at p such that you have something like this. So this is a finite dimensional vector space over QP. Okay, so now the Coleman's theorem says that if you have an overconvergent p-Adic modular form of weight k, and it's an eigenform under the operator UP with p-Adic valuation of AP strictly smaller than k minus 1. Okay, so under this hypothesis, you are going to have actually is f is classical in the sense that f lies in this finite dimensional vector space. Okay. So this result was first proved by Coleman in 1996 and extended by himself in 1997 to a higher level. So I mean, the level like this. And then later on, Basser and Hasse has reproved the Coleman's theorem by analytic continuation method. So I think this work is in 2003, and this is 2006. Okay, so the basic idea is we can just use the functional equation of f equals 1 over AP times UPF to extend your overconvergent p-Adic modular form, which is originally defined in a strict neighborhood of the ordinary locus of the rigid p-Adic of the rigid modular curve like this. So extend this to to the whole rigid unit modular curve, and then you use the rigid Gaga theorem to conclude that you really have an ordinary usual modular form, level gamma 1 and gamma 0 p. Okay. And after that, there are many generalizations of this theorem in various directions. And in 2009, I think Hasse has extended to this theorem to the case of Shimura curves. And in 2010, Sasaki has studied the case of Hilbert modular form, but in the totally split case. So by this, I mean your prime number P is totally split in the totally real field that defines the p-Adic, the Hilbert modular variety. Okay, and then in 2009, so in Vincent Piloni's thesis, he treated the case of GSP4. Okay, so and today my result is you suppose you have a quadratic real field I called F, and P is inert in F. Then we can have some similar result of this kind. Okay, so let me introduce the objects first. So under this hypothesis, the completion of F at P is just isomorphic to the degree 2 unramified extension of QP. And we put W equals like this, and QP square is just the fraction field of W. So I consider the Hilbert modular variety over W with level gamma 0, double 0 n. So I think there are two terminologies in the literature. So someone calls this level structure gamma double 0 n, and someone calls it just gamma 1 n. So it's a natural generalization of gamma 1 n in the classical case. And so its modular interpretation is the following. So for any W algebra called R, then XR is just the isomorphism classes of Hilbert modular variety, of an abelian variety with real multiplication by OF and with a prime to P polarization, and also with a level structure of gamma double 0. And this AR, I usually called it HBAV, like this. Okay, so this is simply denoted by A in the following, because the polarization and level structure will not play an important role in the following story. So now we need also another Hilbert modular variety. So it's the modular variety of level gamma double 0 n intersect with gamma 0 p. So you just add Ivahori structure at the level p. So its modular interpretation is the following. So for any W algebra R, the R valued points of Y is just something like you have your HBAV with polarization and level structure, and together with a subgroup I called H. So this H is a subgroup contained in the P torsion of your abelian variety, and it's called it's stable under the action of OF. So, and usually it's called OF modulo P cyclic. So I mean it's geometrical fiber of this H. In characteristic 0, it's just a FP square vector space of dimension 1. And so you have two modular varieties, and you have a natural projection map from Y to X. So you just forget this subgroup at the level P. And from this data, you can consider similarly the formal completions of these schemes along its spatial fiber. And also you can consider the rigid version of these modular varieties. So, but rig, I mean it's rigid generic fiber in the sense of Renault. Okay, so inside this modular variety, X rig, there is an ordinary locus denoted in this way. So here it's just the locus such that the universal abelian variety has good ordinary reduction. So, and for an ordinary abelian variety, if you consider its p-torsion part, there is a multiplicative part, which is naturally OF modulo P cyclic subgroup contained in this one. So you take your H to be this. And this defines a natural section over the ordinary locus of the projection from Y to X. So you have a Y rig, and it's project to X rig. So here you have its ordinary locus. And now you have a section like this. So section is defined to be H. So you just take its multiplicative part. Okay. And I call the image of this map Y-OC rig. So the natural projection, when you restrict to the ordinary locus of Y rig, you're going to have an isomorphism. Okay, so now suppose you have a pair of integers, k, k1, k2. So canonically, these two numbers are indexed by the two embeddings of f into your base, qp square. So And if you have such a pair of integers, you're going to have a modular line bundle. So line bundle defined in the usual way. So, and I will call mk gamma double 0 n intersect with gamma 0 p to be the global section of y over its generic fiber of this modular line bundle. And similarly, you can define some overconvergent analog of this space. So we can define m dagger k gamma double 0 n to be the direct limit over u. So I will explain what u is of h0 u omega k. So here u runs through the strict neighborhood of the ordinary locus of x in the modular variety x rig. So the rough picture would be something like this. Suppose this is your modular surface, x rig, and the ordinary locus looks like something like this. So this is x rig arc. So you just get rid of some quasi-compact admissible open subset in this thing. And now the admissible the strict neighborhoods of this ordinary locus looks like something like this. So this is your v. So you just extend a little into the non-ordinary locus. Okay, so from this story, you may be curious that why we define just gamma double 0 n. Why don't we just define something like this? But actually, you will get the same space. So, I mean, by the theory of canonical subgroups, this section as not, so will extend to a strict neighborhood of the ordinary locus. So in this picture, actually you can have a strict neighborhood of the ordinary locus, maybe called U, such that this section extends. So in other words, you are going to have a strict neighborhood of the ordinary locus of Y in Y rig, such that the natural projection of this strict neighborhood to U is an isomorphism. So consequently, if you want to define naively this space of overconvergent p-Adic modular form in this way, then it's going to give you the same thing. So, and another consequence is there exists a natural injection from the real modular form of this level to the overconvergent modular form of level gamma double 0 n. And so our situation is completely analog in the Coleman situation. So sorry. And so now the main theorem is the following. Okay, so by the way, there is a UP operator, sorry, on both spaces. And so you can talk about the UP eigenvector in this space. So now suppose you have an overconvergent p-Adic modular form of this level, and you suppose that its eigenvalue under the UP operator with the p-Adic valuation of the eigenvalue strictly smaller than the minimal of the weight, -2. Then F is classical. So in the sense that F comes from this space. Okay, so now I have to make a remark. So just yesterday, after I sent my manuscript to Vincent Piloni and Benoit Stoll, and they told me that they got similar results by some kind of similar methods. So for more details, you can ask him next week. I think basically the same idea. So it's kind of stuff. But I think they got more general results. So that's bad news for me. Okay, so anyway, I need to explain some ideas of the proofs. So first of all, by so-called crucial principle and rigid Gaga theorem, you can actually show that the space of modular forms in the algebraic sense is the same thing as the global section of this rigid variety. Okay, so the point is here you have to apply crucial principle first because this variety is not compact. So you have to first compactify it and compare it with the rigid version of this one. So. And the second thing is called Piloni's trick. So this is introduced by Piloni in his thesis in the Ziegel modular case. So Ziegel case. But here we applied it to the Hilbert case. So, but the idea are the same. So suppose you have a closed coordination 2. So suppose you have a closed subscheme of coordination 2 in the spatial fiber, and you want to compare the global section of omega k over the whole rigid variety and the global section over just the tube along this open subside, then actually you will get the same thing. So you can get rid of a closed coordination 2 subside from your variety Y. And so actually here the argument is a little delicate because the spatial fiber of Y is actually is not normal, but its local rings are all CM rings, so that's fine. Okay, so from the above two remarks, you will say the basic idea of the proof is you need to extend your overconvergent modular form F to the tube of an open subside of the spatial fiber whose complement has codimension 2. Okay, so, and in this process, the key point is to understand the Hasse operator, the UP operator, how it acts on the variety and on the space. So, key point is to understand the action of UP. So first of all, we haven't defined the UP operator yet. So to define UP operator, you need two projections. And this C is the scheme that parameterizes the object like this. So here, H is an object in Y rig, and H prime is a subgroup in the P torsion of A, which is different from H. So actually, you are taking two subgroups in the P torsion of A, and which are both stable under the action of OF, of course. And so you have two projections. The first projection is just associate this triple to AH. And another projection is you modulo this H prime. Okay. So this defines a set theoretical correspondence on the rigid space Y rig. So if you have a rigid point Q here, you're going to associate the site pi 2 of pi 1 inverse Q. So it's going to be a finite set of rigid points. So there are p square elements. P square points, maybe. Sorry. And now suppose you have two subsets in the two copies of Y rig such that pi1 of U is contained in pi2 of V, then you can define the UP operator on the section of omega k over V to the section of omega k over U. So the formula, explicit formula, is something like, if you have an f here, then the UP of f evaluated at AH is going to be 1 divided by p square, and h prime contained in, you sum over all the h prime contained in AP, which is different from h. And you look at the quotient by this h prime. Okay, so the basic idea is, since our f is defined in a strict neighborhood of the ordinary locus, so you're going to use this formula of UP of f to extend successively the domain of definition of f to the whole region. And so you have to study all the other finite subgroups contained in A of P. And you want to look at where the image is. So, okay, so in order to do this, you need a good parameterization of Y rig by partial degrees. So what is partial degree? So suppose you have a finite extension of QP square called K, and OK, it's a ring of integers. Now suppose you have a finite flat group scheme over OK. Equipped with the action of, well, you just need the ZP square, so which is isomorphic to OFP. Now you can consider the invariant differential module of G, so which is defined to be the pullback of omega 1 of G over OK. So this is going to be a finite OK tensor ZP square module. So this guy will decompose into two copies of OK, corresponding to the two embeddings of ZP square into OK. So, and correspondingly, you have a canonical decomposition of omega G into two parts, omega G1, omega G2. And now you just define the partial degrees, for example, degree 1 of G to be the p-Adic valuation of the zeros fitting idea of omega g1. So basically, what we do is you choose an isomorphism of OK modulus of omega g1 with OK modulo some elements called AI. So, and this degree 1 is just the sum of the p-Adic valuation of AI. Okay, so since you have two copies, you're going to have degree 1g and degree 2g. Okay, so now you can apply this idea to the Y-rig. So you're going to have a valuation on this rigid space, parametrized by 0, 1, and this square. So the method is, if you have a rigid point here, you just associate to it the 2 degrees of h. Okay, so the parameter space of Y-rig is going to be a square like this. You have coordinate 1, 1, 0, 1, and here you have 1, 0. This is degree 1, degree 2. Okay, so there are two spatial lines I'm going to explain. Okay, so first of all the ordinary nucleus is going to send to this point. So this is the image of our ordinary nucleus. Because over the ordinary nucleus, the subgroup H is multiplicative, so it's isomorphic to mu p times mu p. And if you consider its degree, it's going to be 1, 1, this. And so if you have an overconvergent p-Adic modular form, the overconvergent p-Adic modular form is going to define in a strict neighborhood of the ordinary nucleus, so it's going to define some area here. And now what you are going to do is to extend the definition, the domain of definition of f to the whole square. Okay, so this can be done in several steps. Okay, so before doing this, let's make a remark is the boundary of the square. So you just put together the four edges. So this boundary corresponds to the tube over an open subset called U in the closed fiber of Y, whose complement has codimension 2. So in other words, you just need to extend your f to the boundary of this diagram. And this can be done in several steps. The first step, you can extend f to accord canonical locus, V canonical. So this is essentially has been done by Gorin and Hasse in the recent paper on canonical subgroups of Hilbert modular varieties. So this V canonical is just the area degree 1q plus p times degree 2q strictly than 1 and degree 2q plus p degree 1q strictly than 1. Okay, so in other words, this canonical area is this part. So you already have two edges. And they studied in detail the dynamics of UP operator over this canonical area. And they show that for any Q1, contained in the image of Q under the Hecke correspondence, you are going to have degree I plus 1 Q1 equals P minus 1 over P plus 1 over P degree IQ. So for any I 1, 2, 1, 2. So I mean, if I is one of the two numbers, then I plus 1 is the other. Okay, so by using this formula, you say when you apply the UP operator, your point Q is going to move towards this point, which corresponds to the ordinary locus. So you apply UP operator successively, you're going to transform the whole canonical region into the region where f is originally defined. So you can extend f in this way. And now step 2 is you can extend f to these 2 points in this picture. So, 0, 1. Okay, so actually, these 2 points corresponds to 2 tubes I call W1, W2. So each Wi is a subset in the closed spatial fiber of Y, which has dimension 2. So these 2 points are actually quite large. Okay, so, and this is one of the key steps. So I will explain later. And the third step is you can extend f to the region where degree 1 is greater than 0, degree 2 is also greater than 0. So I mean, now in next step, you extend your f to here and here. Not so the 0 point is excluded. So these 2 sides. And then last step is you construct a function g, which on the locus with degree totally 0, and you glue g with your extension f along certain strict neighborhood of the 0 locus here. And so this step is essentially due to Hasse. The situation is slightly different, but the method is the same. So I think I should put his name here. So I will just explain these two steps. Okay, so in order to do step 2, you have to understand. So suppose you have a rigid point at this with degree 1 equals 1, degree 2 equals 0. So you need to study where are the other subgroups contained in A of P, which are different from H. So actually, this can be described very precisely by using partial Hasse invariants. So let me first explain what are partial Hasse invariants, or its variant called partial Hodge-Heights. So suppose you have a Abelian variety with an action with real multiplication by OF, and it's over certain over the integer range of certain finite extension of QP square, and you consider its the reduction of a modulo P. So by this, I mean space change over OK modulo P. Then you can consider its Lie algebra of this Abelian variety. So this is going to be OK modulo P tensor with OF, so which is just 2 copies of OK modulo P. So this subscript 1 and 2 means the action of OF is by the first embedding into OK and the second embedding into OK. So and also the Frobenius, since we are in characteristic P, the Frobenius, or rather than Fierschbon, to be more precise, but actually they are the same. From, so let's say Fierschbon, where induces a morphism of OK modulo P tensor OF module. And so you can just you can choose a basis called E1, E2 for these two subdirect summand, so that this morphism I call phi is given by T2 E2, T1 E1, and these two things are usually called the Hasse invariant, partial Hasse invariant. Invariants. of the abelian variety over in characteristic P. Now you put Wi of A equals the truncated p-Adic valuation of Ti. So this Ti is going to be some elements in OK modular P. So here Vp, I mean, it's a truncated p-Adic valuation from this guy to 0, 1. So it's you get a number in 0 and 1. Okay, so here, I mean, anything is killed by P is going to have truncated valuation 1. Okay, so oh, sorry. Okay, so key computation is the following. Suppose you have a rigid point in Y rig with degree 1 of Q. So I mean degree 1 of Q is just degree 1 of H equals 0, and the degree 2 of H equals 1. Then the consequence is W1 of A is necessarily equals to 1, so which means it's killed by P. The Hasse invariant is killed by P, and for any H prime contained in A of P, you can, so which is supposed to be OF mod P cyclic, and H prime different from H, then we always have degree 1 H prime plus P degree 2 H prime equals 1. And actually we have more precisely if you know the second partial Hodge height of A is between 0 and P over P plus 1, then or H prime will has degree 2 equals 1 over P minus W2 of A over P square. So I will explain what does this mean. If the second partial Hasse invariant is between P over P plus 1 and 1, then there exists exactly one H prime, one distinguished subgroup contained in AP different from H, such that degree 2 of H prime 0 is 1 minus W2A. And for all other H prime different from H are going to have degree equals degree 1, H equals 1 over P plus 1. Okay, so what does this mean? This means in this picture, if you have your original point, Q is here, and then, the other H prime is going to lie on this line. Okay, so that's the first part C. And moreover, if you know the partial Hodge height of A is between 0 and P over P plus 1, then all the H prime is going to be just this part. Okay, so the intersection of these two lines, easy to say, is 1 over P plus 1, 1 over P plus 1. And the second part says that if the second partial Hodge height is greater than that value, then there is exactly one lies on this line segment, and all the others are going to remain here. So, okay, so now if you once you establish this proposition, so you just look at the formula UP of F. So it's something over H prime H prime and AP over H prime. So, and if you consider the degree of this image, degree I is going to be 1 minus degree I over H prime. So that means if you have a point here and the orbits under the Hasse correspondence is going to be like on this line, because you flip over the degrees by 1 minus something like that. So you say in most cases we are fine, because in most cases the other subgroups are lying on this line and outside this point. So when you flip over, you are going to in the canonical locus. Well, the F has been defined. So you can just use 1 over AP times UP of F to define, to extend your form. But if there is a subgroup, cyclic subgroup with degree 0, 1, and 1, 0, so you have some trouble. So, and in that case, you have to do some more work. So the idea is, in that case, so if there exists H prime 0 different from H with degree 1 equals 0, degree 2 equals 1, in this case, you need to separate your UP operator into two parts. Okay, so this first part corresponds to this unique subgroup with this degree, and this part corresponds to the other subgroups of degree 1 over P plus 1. So and in this case, you need to modify your definition of your candidate for the extension of F to be something like this one, and maybe you need to consider more, and you need to modify add some terms here to consider the case. Well, if you flip over this point to here, then the situation is again the same, so you have to flip twice, and so on. So no. It may happen that you have to flip infinitely many times, and that's the key point. And in that case, you're going to have a power series like this. So you're going to have your candidate for extension is going to be 1 over AP0 F plus 1 over AP F UPS UP0 F and so on. So if it flips over infinite times, so you need a theory like this. And the condition that the p-Adic valuation of AP is smaller than minimal of K1, K2 minus 2 is imposed such that this theory is convergent p-Adically. So
is it the only place where you use the condition?
Yes, I think so. So this is why we need this condition. And so if you do not have this condition, I think you can extend your F to the canonical part and also a very large area inside of these 2 points. Okay, so I think I should stop here. So, thank you.